If you look at the edge of a black hole, you'll see hundreds of versions of yourself. This isn't magic, it's not fiction, it's the photon sphere. In just 15 seconds, not even light could escape your eyes. Today, we're going to talk about something heavy. What would happen if we threw you into a black hole? And no, this isn't science fiction. It's a speculation based on hardcore physics. Before throwing you in, let's quickly remember what a black hole actually is. Even Einstein, back in his time, described a black hole as the place where God divides by zero. But the truth is, even he didn't believe these things really existed in our universe. And yet, humanity found them. When supermassive, super dense stars reach the end of their lives, they go through a violent transformation. They collapse completely. Nothing remains. What's created is called a singularity, a point in space-time with infinite density and infinite gravity. The theory of general relativity brought us a revolutionary idea. Gravity isn't exactly a force acting on objects. It's the result of how mass bends the fabric of space-time itself. This perfectly explains why Earth orbits the Sun, and why each planet revolves around its own star. Inside a black hole, there is no solid black surface. The singularity, hidden deep within, is so dense. It warps space-time in the most extreme way, forming an almost vertical pit of reality itself. In 1939, Einstein published a paper claiming that the idea of a star collapsing into a singularity made no sense, that it couldn't happen in our universe. Coincidentally, that same year, Oppenheimer. Yes, that Oppenheimer, along with physicist Arthur Snyder, published a paper predicting that a star could indeed collapse under its own gravity, becoming a black hole. Now, let's talk about you. What happens if you fall into a black hole? The most terrifying thing about black holes is that anything can become one. It doesn't matter if you're a star, a planet, or a tiny human being like us. If you compress anything enough to fit within its Schwarzschild radius, it becomes a black hole. German physicist Karl Schwarzschild was the first to discover the exact solution to Einstein's field equations. It's both elegant and terrifyingly simple. Take our sun, for example. If you compressed all of its mass into a sphere just 3 kilometers in radius, boom, it would become a black hole. Earth? It would shrink to the size of a marble, about 9 millimeters in radius. And humans? We'd have to be compressed to a size smaller than a proton. Something absurdly small. But if we could somehow do that, yes, even a human could become a black hole. So, which black hole should we throw you into? We could choose a small one, but that wouldn't be much fun, would it? Better to pick a big one. There are black holes whose event horizons are larger than our entire solar system, with billions of times the mass of the Sun. But that might be a bit much. How about one a little closer to home? Sagittarius A, the supermassive black hole at the center of our galaxy, the Milky Way. You're actually orbiting it right now, as we speak. It's also one of only 2 black holes ever photographed by humanity. Now picture this, you and I fly there together. We park our spaceship 1 trillion meters away from the event horizon, and now we send you straight toward it. As you fall freely, I stay behind on the ship, watching. But here's the critical part. General relativity tells us that time for someone near a black hole moves very differently compared to someone farther away. The black hole warps space-time so much, it bends the very flow of time. This concept was beautifully portrayed in the film Interstellar. To track this, we'll give you a special watch, one that displays how much time has passed, both from your perspective and from mine aboard the ship, clock synced. Your journey begins. As you fall toward the black hole, you watch it from a distance, swallowing matter at terrifying speeds. It's an incredible sight. Matter heats up to unimaginable temperatures due to friction as it spirals inward. If we tried to simulate this scene on an ordinary computer, it would take more than 10 years to render. In reality, this accretion disk would glow a blinding blue-white from the heat. But in most simulations, it's rendered orange, just to make it easier to observe. The first time you check your watch, only 30 minutes have passed for you, and you've completed only 0.1% of your journey to the event horizon. Meanwhile, I, watching from the ship, have experienced just 11 more seconds than you. The difference in time isn't too crazy yet. As you fall even closer, the warping of space-time creates strange visual effects. Light coming from the sides, or even from behind the black hole, bends before reaching your eyes. Check the watch again. Now it's been 2 hours for you, and you've covered 0.4% of the way. Meanwhile, I'm now 44 seconds ahead of you in time. Still small, but growing. The shadow of the black hole, that dark circle in the center, seems to be growing faster than expected. This happens because of gravitational lensing, the warping of light that would normally pass right by you, now being bent directly into your eyes. After a long while, you check the clock again, and now things are getting freaky. From your perspective, 12 hours have passed since you began falling. But for me, I've been watching you for almost 15.5 hours. We're now extremely close to the black hole, and things are about to get really weird. Before crossing the point of no return, you pass through something strange, something mysterious. If time were frozen at that precise point, and you could look around, you'd be utterly shocked. You've reached the photon sphere, one of the most bizarre places in the entire universe. Here, gravity is perfectly balanced. Photons, particles of light, orbit the black hole in a sort of glowing ring. This isn't light reflecting off something. It's literally light trapped by gravity, circling endlessly. If that beam of light shifts even slightly toward the black hole, it falls in, shifts slightly outward, and it escapes into space. In this bizarre place, if you turned around, you'd see multiple versions of yourself. Reflections, of reflections, of reflections. You'd see the back of your own head, multiplied infinitely, staring into the void. You're literally seeing yourself, as if standing next to yourself, in real time. No mirrors, no tech. It's all caused by the mind-bending curvature of space-time itself. As you continue falling, the black hole fills more and more of your vision. It feels like the darkness is swallowing you. That happens because even the back and sides of the black hole are being warped into your field of view. In flat space-time, what would have been visible to you was left behind 13 hours ago. In 24 more minutes, you'll cross the event horizon. Meanwhile, I've already been watching your fall for nearly 20 hours. A few minutes later, you glance at your clock again. I've now been watching you for almost 40 hours. To you, the last few minutes have felt like, well, a few minutes. To me, hours. And now, the final moment arrives. In 6 minutes, you'll cross the event horizon, the ultimate point of no return. You close your eyes, take a deep breath, and check the clock. It looks broken. It shows that I've been watching you fall for an infinite amount of time. But no, it's not broken. That's just how physics works. I've spent decades on the ship, watching you slowly approach the event horizon. I saw your image shift into a deep red, thanks to gravitational redshift. I had to use an infrared telescope just to keep seeing you. And here's the craziest part. I will never actually see you cross the event horizon. Even if I could live forever, those last 6 minutes for you would stretch into an eternity for me. It feels like pure science fiction, but this isn't fiction. This is exactly what Einstein's equations predict. Now you're past the event horizon. So, what happens next? The strange thing is, you barely notice the moment you cross it. You can still look outward, still see the stars, still see our ship floating out there in space. But that light, like you, is now doomed to fall toward the singularity. You've passed the point of no return, the point of infinite density, the point where every law of physics collapses. Even time itself stops making sense. If you wanted to escape the pull of the singularity, you'd have to go faster than light. And as we know, that's impossible. There's a common myth that if you looked outward from inside the black hole, the extreme time dilation would let you watch the entire future of the universe unfold before your eyes. But no, that's not how it works. As you approach the singularity, the entire universe collapses into a thin, bright ring in your field of view. And finally, as you get close enough to the singularity, your feet are pulled forward, your body stretches, you become spaghettified, stretched thinner and thinner, until you are one with the black hole, merging with it, drifting through the cosmos for all of eternity. Just thinking about this entire process sends chills down your spine. And yet, it's impossible not to want to know more. These hidden black holes fascinate us and terrify us all at the same time.